Hello everyone and welcome back to the channel CSAITTL Think Think or Learn. If you're passionate about engineering and want to master the art of building robust, high-performance system, make sure to hit that like button, subscribe, and turn on notifications so you never miss a deep dive. Also, I'm excited to point you toward my companion site, bitbytoken.com. It's a curated hub I built that covers the absolutely core of software, data, AI, machine learning engineering. You'll find foundational concept plus detailed system design breakdowns for each of these disciplines. It's a perfect component for growth. Let me help you with a bit of the navigation here. So this is the bitbytoken.com. The link will be in the description below. This is again several disciplines that I have identified here: software, data, machine, and AI engineering. For each of those engineering, there are several articles which are related to the fundamentals. So you can search them, say for example, WebSockets. Each of those topics are further broken down into basic, advanced, and expert. Further down, we have the example solutions. We have tried to make these solutions as comprehensive as possible. So we have like starting with functional requirement, NFR, scale estimation. We have high-level design, detailed design, covering through the various diagrams, how each of those work together. Then we have data models. Along with those, we try to cover the sequence diagrams. Further down, if you go through that, we are looking for various scalability and availability deep dives, how sharding will work in these particular scenarios, how the caching strategy are supposed to work. Then we talk about the trade-offs and consideration as well. All in all, we have tried to make it as comprehensive as possible, but I would like your feedback on these particular piece. And if there are any other article that you would want like me to add to this list, please do share that in the comments. So let's continue with our deep dive now. Um, okay, so let's go to slide. Okay, to understand caching, we have to respect the physics of scale and latency hierarchy. Think of this as the speed limit for your data. Your CPU L1 L2 cache is blazingly fast, moving in nanoseconds. RAM follows at roughly 100 nanoseconds, while your distributed cache, like Redis, typically operates in a millisecond range. Compare that to your relational database, which you can range from 10 to 100 milliseconds. Moving data from the slow disk-bound DB to an in-memory, in-network cache results in 80 to 100 times speed gain. Remember, your database has finite IOPS. If you exhaust them, the system crashes. The cache is your throughput force multiplier. Its job is simple: shield the database at all costs. Let's define the atomic unit, the hit versus the miss. A hit is the gold standard. It's fast, inexpensive, and most importantly, it bypasses your origin database entirely. A cache miss is expected, but it's expensive. It triggers a full database fetch and subsequent cache warming. Now, here is a critical metric for your system. Your target hit rate should be consistently over 80%. If your hit rate is lower, you are actually scaling. You are just introducing an extra expensive network hop. If you're below 80%, you're likely adding latency rather than just removing it. First up, the industry default, cache aside or lazy loading. In this model, the application is the orchestrator. It checks the cache, and if it is a miss, it goes to the database and then updates the cache. It's highly resilient. If the cache goes down, the system simply fails open to the database. However, there's a catch: the race condition. This tiny window of time between a DB write and the cache invalidation, where a reader might pull stale, outdated data. It's a classic trade-off between strict consistency and a system availability. Next, we have the elegant read engine, read through. Here, we change the architecture so the cache is the orchestrator, not the application. The app simply calls cache.getKey and moves on with its life. The complex, repetitive logic of checking the cache, hitting the database, and updating the cache is hidden entirely within the caching layer itself. This is a massive win for a clean architecture. It removes duplicated, complex code from your microservices and makes your app logic significantly easier to maintain. Now, for the scenarios where close enough isn't just good enough, right through. This is the consistency enforcer. In this model, writes occur against both the cache and the database synchronously. You gain perfect data consistency, but you pay the latency tax. You wait for two network hops on every single write operation. Use this sparingly, like for financial records or inventory systems where the business cost of a stale read outweighs the performance penalty of the latency. In a system design interview, you shouldn't just recite patterns. You should show that you chose the right tool for the job. Use this strategy matrix as your mental model. When asked about caching, pause and articulate your constraints. Do you need a low latency system or is a strict consistency the priority? Are you building for resilience with a fail open design? Never just name a pattern. State your requirement first, then pick the strategy that solves for those constraints. The expiration dial or TTL. Well, it rhymes with our channel TTL, funny enough. This is a passive invalidation, and it's all about finding the sweet spot. If your TTL is too short, you are constantly hammering the database with refetches. If it is too long, you're serving stale data to your users. Think about the data's volatility. Static assets that never change might have a TTL of 1 year. Profile data might need 15 minutes. But for real-time pricing, you might only have 10 seconds. You must match your TTL to the velocity of the data. Now, the warning zone, the thundering herd. This is arguably the most dangerous cache failure mode in production. Imagine a viral item where the TTL expires. Suddenly, thousands of concurrent requests all hit the cache miss at the exact same millisecond. They all race to the database to fetch the same data. The DB buckles, latency spikes, and your site goes down. This is why we don't just rely on default TTLs for high traffic assets. So how do we fix the stampede? We have two primary engineering tactics. The first is jitter. We add randomized offset to our TTLs. This ensures that cache expiration are staggered rather than all hitting at once. The second is the mutex lock. We ensure only one worker is allowed to fetch from the database while others wait. Crucially, always use the double check. Once your process requires a lock, check the cache again. Why? Because another thread might have already fetched the data and bombed the cache while you were waiting for the lock. Active invalidation and key namespacing. This is often called one of the hardest problems in computer science for a reason. Active invalidation means we don't wait for a timer. We explicitly delete data when an event occurs, like a user updating their profile. The golden rule here is never use unstructured keys. Always namespace them. Service, entity, ID, variant. This isn't just about cleanliness. It enables bulk invalidation and prevents catastrophic key collisions across different teams working on the same infrastructure. The macro view, concentric ring of protection. Caching is fundamentally defense in depth. You have the browser, the CDN, the application server memory, and your distributed cache. Each layer serves a different level of granularity, and they all work together to achieve one goal, starving the database of read traffic. Every request caught by a cache layer is one fewer request that risks bringing down your primary storage. The distributed engine, Redis versus Memcached. Memcached is fantastic for pure high throughput string caching. It's simple, light, and does one thing very well. However, Redis provides a much richer set of data structure, persistence, pub/sub capabilities, and Lua scripting. The interview default should be Redis, unless you have a very specific high performance constraint that necessitates if only I can speak today, that necessitates memcached. Redis's versatility makes it a superior choice as your system complexity inevitably grows. Before we finish, beware of these common pitfalls. I'd cache everything is a trap. It leads to a cache bloat and a waste in expensive memory on data that rarely changes or is rarely read. Ignoring invalidation leads to permanent stale data, which can break business logic. Fragile architecture happens when you don't account for a cache failure. Ensure your system can fail open, and unstructured keys lead to key collisions that are a nightmare to debug. These are the traps that turn a junior engineer into a senior one once they have learned to avoid them. The senior perspective is truly about mastering the why. Engineers who stand out don't just memorize when to use jitter or mutexes. They internalize the reasoning behind every architectural decision. They understand the physics of latency and the mechanics of the engine. Once you grasp these fundamentals, you're ready to design under pressure. Now, I'd love to hear from you. What's the biggest gotcha you have encountered while working with the cache invalidation? And how did you or your team handle it? Let me know in the comments below. And do check out our website as I mentioned earlier, bitbytoken.com. The link will be in the description below. If you found this deep dive useful, please like, share, and subscribe to help the channel grow. Thanks for watching, and I'll see you in the next one.